So today we have Professor Van Vu. He will tell us about his work on random matrices with random permutation. So he's going to talk about some new work concerning matrices with random permutation, which can also be viewed as random matrices where entries have arbitrary means. This study is motivated by real-life problems in data science and the theory of numerical computation with many real-life applications. So I'll just go to his biography. Professor Vu is currently Percy F. Smith Professor of Mathematics at Yale University. He received his PhD at Yale under the mentorship of, I think, I'm not very good at Hungarian name, Laszlo Lovas, maybe something like that. Laszlo Lovas is a kind of great expert on combinatory and also computer science. When he was at Yale, he Prof. Vu was at UC San Diego before moving to Rutgers, and he has been at Yale since 2011. He was honored with the Sloan Fellowship, Poya Prize of the Society for Industrial and Applied Mathematics, and the Fulkerson Prize, joined with Anders Johansson and Jeff Kahn in 2012. He's a fellow of the American Mathematical Society, fellow of the Institute of Mathematical Sciences. His research interests include additive number theory, combinatorics, probability, and random matrices. So, Professor Van Vu, please start your talk.
Okay, so today I'm going to talk about something which is, not classical random matrix theory, like, we are going to compute, sort of global or local distribution of certain things, but in some area which have interaction between matrices and randomness, and you will see some classical random matrix theory coming into it, but at a later point. So to the problem this motivates me is very real. There is the matrix completion problem. The most represented example is the Netflix problem. When Netflix have a scoring system, right? So you watch movie, and sometimes we give a movie a score from 1 to 5. So this number here can take any integer. So sometimes half integer from 1 to 5. And now, of course, not everybody see every movie, and so we have a lot of question mark here that, okay, people haven't seen or haven't scored on this movie yet. How can we guess if they like the movie or not, right? So if we guess, and that's how people send, recommendation to you. Say if they can guess that book, give adventure like 5, then Netflix is going to recommend the movie Adventures to Bob. And this is a typical scoring system or recommendation system now in industry. It's not only for movies, but any kind of commercial products that you can see, right? That people really want your opinion on some product, and so that they can recommend them to you. Okay, so the mathematical statement is like this. We have a data matrix, and which is not square matrix typically. So N1 is a set of user, and N2 is a set of products, for instance. It has some singular value decomposition. And the problem is that we don't see every entries of this movie. We see only few of them, right? So it is sort of a random sub matrix of the original matrix. Every entry is observed with probability P independently. Well, we assume that. And so we see only a P fraction of the entries. Yeah. So if we see this and then we see the real value of the entry, like Mij here, and otherwise we just write 0. And the goal is to recover the original data, the original matrix, either exactly or approximately from this random observation. So I hope the statement is quite clear and the motivation is really realistic. So yeah, then that's the huge examples from industry and everyday's life that where this problem appears. Say, the collaborative filtering from Netflix to Spotify to Amazon, social network recovery when they want to recover network from few observations, data imputation, like consider health data, which is often bad and incomplete, but then somehow you want to get a better picture of the patient, right? And localization from incomplete pairwise sensor measurement. So I just take this as an example from engineering. So it's not only about personal data; it can be engineering data. So it's a problem with huge importance, and it has been studied quite heavily in the last 20 years. Generally, the problem is of course infeasible. So we need some assumption about the matrix, right? And the most popular and natural assumption nowadays is that the matrix have low rank. Namely, the rank is much smaller than the dimensions n1 and n2. And from now on, I call the rank R, right? And typically, if we are really lucky, then we need only, say, R times the dimension to get the matrix. We don't need the product of the dimensions. And the motivation, or actually the reason for this low rank assumption is that usually things are determined by only a few features. For instance, the movie ratings is determined usually by your age, gender, occupation, type of movies, and another 20 sort of things that matter to you. And this compared to the number of viewers in order of billion is very small, right? Yeah, so the key point is that here low rank is something that's going to help us because that is a small number, and computing with small number is easier than computing with large number. Okay, so here's a small example. Like we have a 3x3 matrix, and we set P equal 1/2, and then we zero out about half of this matrix. Yeah, so here's the bunch of familiar definition: the spectral norm, the infinity norm, the Frobenius norm. I call n is a maximum of n1 and n2, and typically we assume that these things are sort of comparable. And P is a sampling density. One important parameter here is the gap between the singular value of m. Say I order the singular value from sigma 1 to sigma 2 to sigma r, and the gap delta s is between sigma s and sigma s plus 1. And finally, there's the norm that maybe some of you haven't seen, is the nuclear norm, which is the sum of all singular values. So in this case, the sum of all the sigmas, right? Which is also a norm. There's also a notion about subspace perturbation. So here you see one subspace is turned a little bit with some angle delta, and you have a different subspace. Okay, so which matrices can be recovered? Now, apparently you see an issue when the original matrix is too sparse. Say if already have only exactly one dominant entries and all the rest are very small. And let's take P to be 110. And actually you will never hit that entry, right? You hit that entry with very small probability, and all the entries you hit will be unimportant entry. So in this case, there's no way to recover the matrix, right? Because you miss the most important information. Now, in order to overcome that, people, I think, starting with Candace and Reich, introduced the notion of incoherence to address this issue. And basically, they are saying that all the entries of the matrix behave in the same way, but mathematically, it needs a few formula. Yeah, so the incoherent is small, meaning that the principal subspace of M is not aligned with any standard basis element. Or in other words, the observed entry provide approximately the same amount of information. Right. So that's exactly they needed to avoid this bad case when you have one dominant entry. Yeah, so technically, if I denote PU by the projection onto the subspace spanned by a set of vector U, then we and these are the singular vector of the matrix, then we expect that the projection of the basis vector EI is small with respect to U. Right? So PU EI to be small. Right. So here's a few, sort of technical assumption, but it's basically the mathematical realization of what I just said in words. So we denote by mu, mu1, mu2, mu0, various kind of incoherence parameter. But you can see here that basically they say the same thing. For instance, this one here, E of A times PU E of A prime minus this, which is the expectation, is small. Right. So basically, they just say that what I define, or maybe the most important one is the first one, when you have PU EI square, and if this guy is, did U have dimension R, then in the random case we expect this to be R over N. So, and if mu U is 1, then actually we expect that UI behaves sort of randomly with respect to this subspace. And so the small mu is, the less aligned EI is compared to the subspace U. Yeah. So here's just the intuition behind this. But you don't need to really remember them. Anyway, the goals of the algorithm is what? You want to do either an exact or approximate recovery. Approximate means that we have a few errors here and there. And in this talk, we will focus on exact recovery, namely that we have exactly the matrix which was hidden in the beginning. Now, if we run algorithm, we care about the running time, of course, and the simplicity of the algorithm. The one thing people really care about is the sparsity of the data, namely how many observations do we need in order to recover the original matrix, right? This is a parameter that we will mention a lot. It is clear that for exact recovery, it needs observations in every row and column, right? If a row and column is empty, then there's nothing you can do there. So by the coupon-collector, theorem, you will need at least about n times log n observations. So remember this n log n, that what you observe cannot be sparser than this. And then sometimes people measure the quality of the theorem on how close you get to this lower bound. Okay, so there are several approaches to this problem. The first one is by Convex and Reck, that they use convex programming approach. And what you have to do is to fill in, well, imagine that the matrix have low rank R and you see only part of it. So what you really have to do is to fill in the rest of the matrix, so the rank of the matrix is small as possible, right? Now that is a discrete problem, optimization problem. It's very hard, NP hard, basically. So people avoid that by not to maximize, not to minimize the rank, but minimize the sum of the singular values. Intuitively, if the sum of the singular value is small, then sort of you expect that the rank is small too. So this is an idea. I think it did go back to the Candace-Tao paper on signal recovery, which is quite famous. Yeah, so nuclear norm minimization is a convex relaxation of the low rank matrix problem, and the convex relaxation is easy to solve, at least from the from the programming point of view. Any convex program can be solved in linear polynomial time. Now the problem is that convex programming is solvable in polynomial time, but only theoretically. In practice, it's not very effective. So if you want an usual computer give you a result within 1 minute, which is pretty long nowadays, if you have to wait the computer to do something for 1 minute, then actually you get nervous. But in that case, N1 and N2 should be like 100, cannot be more. So it is the limit of this method. On the other hand, the theorem has a nice form. It says that, okay, assume some incoherence assumption. You can have exact recovery if the matrix M is the number of entries you observe, right? M is the number of sample entries. So M is at least N times log N, which is the lower bound. We cannot do better than this, but you are off by a factor N to the quarter. And okay, assume all the mu are constant to make them simple. So, but you are off by N to the quarter compared to the best lower bound. Now this was improved by Candace and Tao, but it caused a stronger incoherence assumption. So I mentioned a lot of incoherence assumption before, and I think all of you forget it, but they just say stronger and stronger thing about how the entries are related to the subspaces. But the point here is that if you have the strongest, I think the strongest incoherence assumption, which actually not very easy to imply on real data, then you can have exact recovery matching the n log n. Okay, it's not exactly n log n to the 6, but never mind, some extra log. Then this famous result say that, yeah, you can match the lower bound. That's why it get very well known, because that is the first one, probably one of the first one to get the correct lower bound. But the cost here is, again, that really strong assumption on the incoherence, that sometimes you may argue that, okay, it is something really happened in real life. Right. Okay, so I ignore the noise part and go to the second method. Okay, so we look at the problem as an optimizing problem before, like you want to fill in the entries in order to make the nuclear norm of the matrix as small as possible. Now, there's a different way to look at the problems. Again, using the assumption of low rank. Now, if the matrix has rank R, then the matrix is the projection of itself onto the subspace spanned by the first R singular vectors, right? It's just by definition. The R singular vectors, or in the symmetric case, the R eigenvectors will span the whole subspace of the matrix. Now, it is a technical sort of notation here that M prime is a normalized version of the observed matrix. So namely, if I observe an entry, I will blow it up by a factor of 1 over p. So because I lose all the entries, I don't observe, right? I make them to 0. So I want to keep the mean of the entries be the same. So I blow up all the other entries, so just to make the sum of the all the entries are the same. For instance, if I zero out this guy, then I will double the rest. Right? So you, instead of 5, you have 10. Instead of 8, you have 16. And the only reason is that the expectation of M prime is exactly M, right? I see everyone with probability P, and when I see them, I blow them up with a factor 1 over P. Now, because expectation of M prime is about M, M prime is sort of an unbiased estimator for M, then you hope that actually the projection of M prime onto the subspace by R largest singular vector will be approximation of the corresponding projection of M. Right? So philosophy is simple. M prime is an unbiased estimator of M. So you do something to M prime, you get some result, and you think that result will be a good approximation if you do the same thing to M. Right? That is the principle of what we're doing everything. And here's the hope, and that's the high hope, because projection is a tricky thing, but the intuition is very natural. Right. So let's see how random matrix come here. What is M prime? Because the mean of M prime is M, so actually, if we subtract M prime from M, you have a mean 0 matrix, right? So M prime equal to M plus E, where E is a random matrix with mean 0 and independent entries. And the entries you can define. It is what we have. Yeah. Yeah. So here's where random matrices enter the picture. That you have a matrix with arbitrary mean, which is M, can be any matrix, and we have a random perturbation, E. And we expect that the matrix with a random perturbation behave similarly like the original matrix in some way. Right? That's the whole philosophy of my thinking, and that underlie all the math that follow. And so this kind of projection estimation has been studied before. There's the very well-known theorem result in numerical analysis called the Davis-Kahan sine theta theorem, which give you some estimate for this approximation. Right? The theorem typically for numerical analysis is for deterministic matrices. So it say that if M, you have a matrix M and perturb M by some matrix E, and now consider the projection on the first S singular vector, then the difference between these two projections, C-net operators, is bounded by a constant times the norm of E, which is sort of natural because the norm of E have to play some role, right? The bigger the noise, then the worse the approximation. Now, what it divide on, it is interesting. It divide by the gap between the S singular and the S plus 1 singular values. So it doesn't divide by the singular value itself. It divide by the gap. Now, in order to see why the gap appear here, let me give you an example. Now, the very interesting thing about Davis-Kahan theorem is that it tells you that singular vector, or actually eigenvectors in this case, because I take example on the symmetric matrix. Eigenvector is not a continuous function. We know that eigenvalues are continuous function. We change the matrix a little bit, the eigenvalues change a little bit, right? But you change the matrix a little bit, the eigenvectors can change hugely. Here's the example. I start with this matrix, 1 plus epsilon, 1 minus epsilon on the diagonal. I change each entry by almost epsilon, right? I get into the right-hand side matrix, 1, 1, epsilon, epsilon. Easily, you can compute that the norm of E is order epsilon, because all the 4 entries are order epsilon, just of different sign. Now the eigenvalues as seen here is seen 1 plus epsilon and 1 minus epsilon. But the eigenvector of the first one is the 0, 1 and 1, 0 vector, right? The first eigenvector is the 1, 0 vector. They are basis vector, no matter how small epsilon is. But the eigenvectors of the second one is 1 over square root 2, 1 over square root 2. It's the 55-degree rotation, right? So it's quite amazing that you see that doesn't matter how small epsilon is, the eigenvector will change a lot. It changed by 55-degree period. You cannot avoid it. And this match the Davis-Kahan theorem, because here the point is the gap between the eigenvalues, right? 1 plus epsilon and 1 minus epsilon is only 2 epsilon, so it's too small. It's the same order of magnitude of the norm of E. So yeah, you expect that this bound on the right-hand side here have to be a constant. It doesn't go to 0 with epsilon. Any questions so far? Okay, if no question, let me continue. Okay, so the algorithm based on this kind of philosophy was done by various group of researchers. For instance, Keshavan, Montanari, and O make the following algorithm. Well, they compute the projection, as I said, of M prime. For that, you get an approximation by Davis-Kahan theorem. And then you clean the estimate to get an exact recovery, right? So remember, Davis-Kahan give you only an approximation, and after that, you have to do something to get the exact recovery. And they do some cleaning step. The cleaning step is well, we will not go into there, but it's basically minimizing a loss function. And can be done very quickly with gradient descent. Yeah, so here's the theorem that they prove. First of all, they assume that the rank R is null, and they have to care about a parameter called the condition number, which is a ratio between the largest singular value and the smallest singular value. Now, this condition number is of critical importance in numerical analysis because it's all kind of precision in calculating depend on it. And they also assume that N1 and N2 is of the same magnitude, which is okay. The theorem say that you can do exact recovery with high probability with the number. So the content of the theorem is always about the number of observations, right? Here, the number of observation is M. And here you see the N here, and N times log N is what we want, which is very nice. On the other hand, you are off by a factor of kappa squared, which is the square of the condition number. And in the worst case, you can get even kappa to the 6. So kappa squared times kappa to the 4 is kappa to the 6. And in general, nothing guarantee that kappa have to be small. In fact, in many cases, the matrix can be a little bit ill-conditioned. And imagine that kappa is only like n to the 1/10, which is really small. Then you are already blow up the whole thing by square root n, right? Kappa to the 6 is bigger than square root n, and then actually we lose a lot. So there's another idea by Chattery that he used thresholding, namely that you don't have to use all the singular value, but you use only the important one, namely the big enough one. And in that case, you can avoid. In that case, you can avoid the kappa to be big, right? Because you already delete all the small singular value. Sorry, some battery. Okay. Yeah. So the idea of Chattery is that okay. We only use the singular value sigma I if it is bigger some threshold, and run the algorithm with it. But then, but there's some assumption you need here, so you have to pay some other kind of cost, namely that you have to assume that all the entries are bounded in the same interval, and it is only an approximate recovery. It's namely your approximation is in Froebel's norm, so it will make a global error on the estimation. All right, so these are more or less the key developments on this problem in the last like maybe 15 years. There are many other versions of this, but I hope I capture some of the main ideas. But the new idea here is, which I want to introduce in this talk, is that we have a matrix with random perturbation, or you can understand it a matrix with random matrix with arbitrary mean. The key observation, which I started this kind of direction about 15 years ago, is that perturbation bound, such as the Davis-Kahan bound, can be improved quite significantly when the perturbation is random. So let me illustrate it by probably the most basic example you can think of about perturbation bound, which is the wave bound, right? We care about the spectral norm of the matrix, and you perturb a matrix by E, you want to know how much the spectral norm change. And we know that the norm of M plus E is at most the norm of M plus the norm of E. And we have the left-hand side, similar left-hand side as well. So the norm changed by at most the norm of E. We all know that, and we use it in everyday life. And we know that it's also sharp if M and E share the leading eigenvector, right? So if they share a leading eigenvector V, then the norm of M plus E is just the norm of M plus E times V, which is the norm of MV plus the norm of EV, and it is just the sum of the two norms. So now come the randomness. If E is a random matrix, then actually the eigenvectors of it are random, right? So the leading eigenvectors of M and E, they should be more or less orthogonal, right? They should not be the same. That's obvious. We can even prove that. We can prove that in many forms. Okay, so now if we fix a vector V, and look at the calculation before, but assuming that MV and EV are almost orthogonal, right? Then we would have this. Let's say MV is lambda V when lambda is the eigenvector of M, right? So M plus E times V is lambda V plus EV. And because they are orthogonal, then by Pythagorean theorem, it would have the square root of lambda squared plus the norm of E squared. So you basically have lambda over E squared over lambda, or 2 lambda. It doesn't really matter. So it's a significant change. It will not be E, but it will be E squared over lambda. And if typically lambda is dominating because E is sort of noise, and we don't expect that the signal of the noise is bigger than the signal of the original matrix, then the second term is much smaller than E itself, right? The norm of E divided by lambda should be much less than 1. Okay, this actually is a theorem. Quite a well known actually by Beynach-Georges and Nadakuditi about 10 years ago. They consider GOE and consider a matrix M when the lambda of M is at least half, more than half the norm of E. Then actually with high probability, the norm of M plus E would be this number. It's very close to the formula you see below before. It's just some difference between the constant. 1/2 here become a quarter. And this is a continuation of something most of you probably already seen. It's called the BBP, Beynach-Georges and Pesce threshold phenomenon, that after you add a matrix to a random matrix, when the sum still behave like a random matrix, right? And so what they found is that if C is less than half, then the sum still behave like a random matrix, but C is bigger than half. Then you see the signal of M from it. So they take this problem the other way around, as I do. So they look at deterministic perturbation of the random matrix. And I look at the other way around, the random perturbation of the deterministic matrix. But the phenomenon is, I mean, at least the formula looks the same. The calculation, the E squared over lambda appear everywhere. And it comes from what I said, the phenomenon that the two eigenvectors have to be orthogonal. And so the case we really care about is that the perturbation, the random perturbation is sort of small compared to the signal matrix. That is the dominating case in reality. And that's good for us, because if the random perturbation is too big, then there's nothing to measure. Yeah, so we assume that lambda is at least, half of E. Then we can bound this. This almost also 10 years ago by Sonorup, me and Kivan. So we show that the norm of M plus E is almost lambda times E squared over lambda. So it matching this kind of calculation, but remember this calculation is fake because here we do the calculation for the eigenvector of M, and we bound this, but the eigenvector of M have no reason to be the eigenvector of M plus E, right? So if you bound M plus E times V by this, it doesn't mean that the norm of M plus E have to be smaller than this, right? But in the theorem, we really prove that, again, with some small difference in the constant term. Now come a very important sort of observation about low rank. Now, typically, well, we talk about E to be a random matrix with independent And in our case, they are not necessarily IID entries, but let's say that they are bounded or sub-Gaussian entries. Then typically the norm of E is order square root n. So the Davis-Kahan bound would give us a bound, which is a norm of E over the gap, right? So square root n over delta S. Now the observation I try to push for years is that if M is of rank R, small rank, then the action of E of the random matrix happen effectively in only R dimension. It doesn't happen in N dimension. So actually the real thing should happen is not the square root of N, it has to be square root of R. Which is sort of intuitive, but not obvious at all to prove. So recently we prove it. It's a long process because in the 2013 version that we have an extra error term, but now we remove that error term and get this kind of result. Which is more or less close to what I want, namely the bound would be really square root of R over the gap, and with some log, correlation, log correction. And the second term we have to take into account is the norm of E, but now not divided by the gap, but by the signal itself with the sigma S, which is a singular value. And you cannot avoid this term either, because if the signal of the random perturbation is bigger than the signal of the matrix, then actually there's nothing there to measure. Okay. So basically that's it. We get almost the optimal bound here under some condition, but I hide the condition. Now it leads to a new way to attack the original problem, the matrix recovery problem. And the new way is the method by approximation in infinity norm. So we will approximate every single entries at the same time, right? So with my student Bhardwaj, we managed to bound the difference between the two projections. So recall that we bound this difference by the Davis-Kahan theorem, right? But now we have a new improved Davis-Kahan theorem. We have a better bound, and in fact they can bound it in infinity norm. And so the assumption here is that, let's say M is a matrix with constant rank and bounded integer entries, which is the case for Netflix problem, right? So the entries are integers or half integers between 1 and 5, and it is the case for every single consumer product rating problems. Now the algorithm is that, again, we threshold at some point. If we find a singular value S plus 1, which is small for some given parameter, then we threshold there and do not use the projection PR, we just use the projection PS. Right? We throw away the not important information. And the matrix and the algorithm is simple. You compute the projection. The rounding actually make very small, difference. The thresholding actually make a very small error because we just throw away quite a very small singular value. They do not contribute much to the entries. And after you get this, you do the simplest cleaning. You get an approximation, right? Similar to the Montanari et al. Algorithm, but now the cleaning process is very simple because we assume the entries are bounded integer, so we just round them to the nearest integer. And so what the theorem sort of guarantees that the infinity norm bound is less than 1/2. So when you round it to the nearest integer, you get the correct value. Okay. Yeah, so here's the theorem. We again have to assume some incoherent assumption, but I think this is the weakest one. And importantly, if you have n time log n entries observed, then you have exact recovery. So you don't have the extra term like kappa to the 6. You don't have to care about the condition number anymore. And you don't really need to know what R is because you do thresholding. So we just go until you see a small singular value and you throw the rest out. And yeah, so there's no kappa, so you can tolerate that condition number. More importantly, it probably tell you that the condition number is not a very important in this kind of problem. And the algorithm is as simple as you can imagine. Okay, so for the rest, 5 minutes or 4, let me tell you another application which can come out of this kind of project, which is the opposite end of completion. It's called the matrix sparsification theory. Now, in the matrix completion problem, the matrix is sparse because we only have a few observations on the data, right? Everybody see only a few hundred movies. Now, in the sparsification problem, you have a big matrix, a full matrix, and you want to compute with it. But compute with a big matrix is costly. So people have a great trick that randomly sparsify a matrix to make a matrix we have almost every entry 0. They keep very few entries at every row, like log n entries at every row. Right? And if your matrix is full of 0, the computation is really fast. And then we come back to that problem that we had before. We have a matrix M prime, which is a random sparsification. We want to compute Fm of the original. So we compute Fm prime and see that, okay, what is the difference? Right? And here the story is, well, the application is different, but the mathematical we can apply the same. Is you can do the same math that or we can do the same math that we did before and have similar result for this case as well. And this is another application of the new math. And this is another area that people in computer science that really talk about. Okay, so I think this ends my talk. Thank you very much.
Any question for the speaker?
So can I ask a question?
Yes, please.
Hi. So very interesting talk. So so in your end result, you still have like, is it true that you still have like a singular value gap? Like you need the singular value of M to be like kind of distant apart. Like, is it possible to remove it if you just want to recover the matrix M instead of like the Eigen space?
Actually, as an example of the 1 plus epsilon, 1 minus epsilon matrix that we showed before, and probably you need some assumption on the gap, right? Because
right, it's like you don't recover the eigenvectors, but you can recover the matrix, right? Like, so that's the kind of different. Or is it actually difficult?
No, you cannot do that because, well, I mean, the intuition is that if the gap is too small, then actually you will mix up the 2 eigenvectors which are close to each other, right? Then you will project your matrix on 2 different subspaces. One is correct and the other one cannot be correct.
But I mean, if you do a summation of those, if, for example, if you, let's say you project to the first 5, right? So then actually doesn't matter if you mix up the first one and the second one because you projected.
Yeah, I know. You only need the gap between the 5 and the 6.
Oh, okay, I see.
Yeah, that's the theorem. Yeah, because the first 4 you don't care that their orders are mixed up. But you mix the 5 and the 6 and you are in trouble.
I see. And how about like suppose you don't know the rank of the matrix, is it possible to work? Like, can you does your method work if you just use a larger than the true R, like, right? If you
yeah. So in this algorithm, we do thresholding. So we just go until you see that everything under that certain threshold is very small, then you just forget them. You don't know the real rank. Yeah.
Thank you.
Yeah, thank you. It's a nice question. Yeah.
If there's no more question, can we thank the speaker?